Okay, so for today, I just want to do a quick review of some really basic Algebra 1 concepts. It's been months since you've done math though, so it's probably a good idea maybe to talk about some of this stuff. And I think even though this is review, I think we'll add a few pieces that might even be a little bit new to you, or an extension of what we talked about before. So the focus of today really is I just want to talk about two things. I want to talk about real numbers, how we slice and dice real numbers, how we talk about real numbers, well, real numbers. We'll get back to that. And then the other thing is I want to talk about some properties of real numbers, some ways that when we do addition and subtraction, and in particular, some patterns and properties that we can see recurring with real numbers. Okay, but start off, let's just talk about real numbers. What are real numbers? Whole numbers are included. Say it again. And actually, real numbers can be negative. I'll make that first question. I'll answer it for you. I'll make it real simple. Real numbers are every number you have ever dealt with in any situation, at any time, in any capacity. Anytime you've ever used a number in any math class, or outside of any math class, it's been a real number, right? Have you ever heard of anything that's a non-real number? Probably not. Probably not. Are there non-real numbers? There are. We're going to talk about them in this class this year. But that's a discussion maybe for a little later time. We'll get there. But for now, we're just going to focus on all the numbers that you know and love, right? The real numbers. So we're going to talk about the set of real numbers and its subsets. What's a set mean in math, first? Talk about a set. I mean, it doesn't have to be even in math. I talk about a set. What am I referring to? A group. A group. That's a great definition. A group. Right? A group of, in math, we'd say a group of elements, a group of things or elements that we're going to collect together. It doesn't have to be, in math, usually it'll be a set of numbers probably, but it doesn't have to be. We could talk about sets of other things. Like, let's just consider the set of all the dishes in your house. Okay, that's a grouping of a bunch of stuff. The elements of that set would just be the dishes, right? Okay, what's it mean to be a subset? Small, say it again. A smaller group within that set. So like a set within a set, very good, right? Set that's included inside a larger set is a subset. So can anybody think of what maybe if we're talking about the set of all the dishes in your house, what's a subset of that group? Cups, or forks, or plates, or something like that, right? Bowls. Something that's a set that's included, completely included within the set of dishes, but there are some other dishes maybe outside of that set. So what if we say the set of bowls, right? The set of bowls is a subset of the set of dishes. It's a set, but there are some other dishes like plates and forks that aren't dishes, right? Okay, so we get the idea. So there are some subsets of the set of real numbers that we use a lot in math. And let's start with the smallest of these subsets and sort of work our way up, okay? So the smallest set is the set of natural numbers. The natural numbers sometimes are called the counting numbers, and they just start at 1 and they get larger. They increase by 1 with every new element. Right, so it starts at 1 and then 2, 3. What's it mean in math when we have a dot, dot, dot? Keeps going, following that pattern, and so on and so forth, or etc., or something like that. Okay, so this represents the set of natural numbers. Now, first thing I want to point out, and this is something we'll talk about throughout the year in math. In math, we try to use as few words as possible. We want to be as unambiguous as possible, meaning we don't want what we say or write in math to be open to different interpretations. We want it to mean exactly one thing for everybody, right? And so this is the way in math, it's one way that we write a set. Whenever you see these script brackets like that, that means in math we'd say the set of whatever's inside, okay? Is there a smallest natural number? What is the smallest natural number? 1. What's the biggest natural number? It goes on forever. There isn't one, is there? It's unlimited at the top end, isn't it? Right? There's no limit to how big a natural number can be. So how many elements are there in the set of natural numbers? Infinite. It's an infinite set, okay? What about the set of whole numbers? It's a slightly bigger set. The set of natural numbers is a subset of the set of whole numbers. So it's slightly smaller. What's the only thing we have to add to the set of natural numbers to get the set of whole numbers? 0. Yeah, you can see that, can't you? Here's inside the set of whole numbers is the set of natural numbers, right? It's a subset. There's one additional element. So how big is the set of whole numbers? Infinite. There's an infinite number of elements in that, right? Which is bigger then, the set of natural numbers or the set of whole numbers? Okay, I'm here. Anybody want to say something different?
Neither.
I'm hearing a neither. I'm hearing the set of whole numbers. They both make sense, don't they? What's your rationale for why neither?
Because they both go on infinitely, so you couldn't tell how much.
They're both infinite, right? And so how could one be bigger than the other? It's a good line of reasoning. Anybody want to defend why maybe they think the whole numbers is a bigger set?
Because the infinite number of natural numbers is included inside natural numbers.
Okay, yeah. So it's a good argument you could have. In mathematics, there is one correct answer here, though, and the answer is whole numbers is a bigger set. Right, here's one way to think about it. It's tricky, though, isn't it? I'm not kidding you. I could teach a class on nothing but infinity, and we could talk about it every day and here all year and never repeat ourselves and still not even get close to covering the topic. I mean, it's a huge topic, no pun intended. There's a lot of stuff to cover there. Right, think about it this way. There's a one-to-one correspondence between all of these elements, right? But when I pair those up, there's always going to be, no matter how far I go, there's always going to be an additional element to the set of whole numbers, which makes it bigger. How much bigger? One bigger. Yes, ma'am.
So you said it's infinite. So the highest number that people have gotten to, how will it be infinite if you don't know it?
So, okay, so what is infinity? Now, one thing we need to say about infinity right away is, and this is something we do, it's an easy mistake that people tend to make with this, and that is they think of infinity as being a number, right? It's not. Infinity just means there is no limit to how high the numbers can get. It's big without limit, right? So there is no highest number that we've ever gotten to because I can name a higher one, that number plus 1, right? See what I'm saying? You can't ever define something like, say, now we could say the tallest mountain on Earth, or the furthest we've explored into space, or something like that, but you can't ever say something like the highest number we've gotten to, because as soon as you stop, you've already got another bigger one. It's that one plus 1, right? It's already implied, okay? So it's a weird concept. Here's another one. This will blow your mind. So let's say that I can infinitely subdivide space. Modern physics tells us that's probably not true. You get down to a small enough distance called the Planck length, 10 to the minus 46 meters. Physics tells us that probably that's where length stops, and you just can't get any smaller. The universe gets weird at that point. There's no such thing as length. But let's assume that's not true. Let's assume that we can cut something and cut it in half and keep cutting it in half and make something as small as we want to forever. If I take the rest of time for eternity, and every second I'm going to cut my distance to the door in half, do I ever get to the door? I don't, do I? Because I'm always just cutting that distance in half. It's always a little bit less, a little bit distance still to cover, right? Okay, let me ask you this. If I take, not just a fine tip Sharpie, but an infinitely fine tip Sharpie, I'm going to start right here. So somewhere between my feet right now and the door, I'm going to make a mark on the floor with that infinitely fine Sharpie. Is there any place on the floor that I could make a mark, as long as it's actually not on the door? Is there a point I could make on the floor with my Sharpie that I would never either step on or step over as I move towards the door, as I described a second ago? You get my question? I'm going to make, it's like saying this. If here's the, so here's the floor, and here's the door, and here's where my foot is starting. if I take an infinitely fine black Sharpie, is there any point that I could draw on the floor that isn't touching the door that I wouldn't eventually step on if I'm gonna cut my distance to the door in half with every step? Step on or step over. Right, obviously I'm gonna maybe step over that one. If I put it right there, eventually I'm gonna step on it, right? Is there any point I could draw on the floor I won't step on? No, and yet I never get to the door. Isn't that weird? It's kind of a paradox, isn't it? Are you thinking, come on, I'm such a dummy, just put it on the point next to the door, right? And I'd never step on that one, could I? But is there a point next to the door? What do you think? Is there a point, what if I just zoom in closer? Is there gonna be a point next to the door? If I think I got the point next to the door, when I zoom in, how many points are there remaining still? Infinite, right? Not weird. Get the idea? That that's a weird, I mean, it doesn't seem like a big deal, but if you really ponder that for a second, that's a pretty profound idea. That there's no place I couldn't draw on the floor that I wouldn't step on, and yet I never get to the door. Weird, right? Okay? All right, so back to this stuff. Okay, we got the set of whole numbers. We add 0. What about integers? What are we adding to the party here, adding to the set of whole numbers to create a bigger set that includes it, that we now call the set of integers?
Negatives.
Okay, all the negatives, maybe like say the negative natural numbers we're going to add, right? And so now this one goes on forever in the negative direction and the positive direction. So one way to sort of visualize the set of integers would be to say it's all the hash marks on a number line, let's say, okay? So far, so good. Now we get to some weird ones, a little weirder. What about the set of rational numbers? Remember what that's all about? And I'll give you a hint. The title really says the whole thing. It really gives away the definition of rational numbers. You fill in the blank. Rational numbers are any numbers that can be written as ratios. What's another fancy name for ratio? Fraction, yeah. Right? Any number that can be written as a fraction is a rational number, okay? We can say that mathematically. Let's sort of dissect this statement mathematically again, right? This is written in mathematical language, what did we say that these script brackets mean? Set. Good. So that's saying the set of, now let's go further. The set of what? The set of m divided by n, okay? The set of m divided by n. Now here's another weird one. When you see a vertical bar like that in math, what does that mean? Any idea? It seems like it'd be divided by, but it's not. It's the same thing it would mean if you were doing some coding or some programming, when you see that. It means the set of m divided by n, and that little bar there means such that, or you could even maybe say if. I like to say such that. And then all this other stuff at the end. Such that m and n are integers, right? Isn't that how you build a fraction? How do you build a fraction? You're going to take an integer divided by an integer, aren't you? To build a fraction, right? Okay, so rational numbers are just the set of m divided by n such that m and n are integers. What about this last little piece at the end? How come we have to include that? And n does not equal 0. What about that n? Why is it so important that it's not 0?
Is this a natural number?
Well, I mean, it could be negative too, but it can't be 0. N can't be 0. How come? No, bingo. You can't divide by 0, can you? There's two things you can't do with real numbers that we'll talk about again and again all year. You can't ever divide by 0. You can't divide by 0. And you can't take a square root of, no, square root of 0 is just 0. What can't you take a square root of? Something you can't take a square root of. A negative number. Yeah, you take a square root, what's the square root of 4? 2. Square root of 0 is 0. Square root of 1 is 1. Square root of 100 is 10, right? What's the square root of negative 4? Got a problem, right? Why is the square root of 4 2? Because 2 times 2 is 4. 2 squared is 4, right? Why is the square root of 0 0? Well, because 0 squared is 0. But the square root of negative 4, what squared is negative 4? If I square something, can it be negative? If I square a real number? No. If I square, like negative 2 times negative 2 is positive 4, isn't it? Right? You get the idea? Okay. Okay, one other thing, it has to do with rational numbers. So if we turn a rational number into a decimal, what always happens? 2 things that could happen. Let's think of examples. Give me an example of a really simple rational number. Simple fraction. 2. Okay, make it one that's not an integer, though. 2 works, I guess, but think of one that's not an integer. A really simple one. What it? 1/3. Yeah, there's one. So 2 things can happen. If I write a rational number as a decimal, 1/3 equals 0. What? 333, and so on. How do we write that usually? Okay, good. 3 with a bar. The bar means it's repeating, right? So one thing that could happen is the decimal could repeat. Okay? Let's give me another, maybe a different kind of fraction. We're going to get a different result. 2, say it again. 2 over 4. There we go. 2 over 4, what's that as a decimal? 0.5, period, right? That's the exact answer. So it terminated. 2 things can happen. Either the decimal is going to terminate or it's going to repeat if it's a rational number. Okay? So does it make sense then if we want to go, let's take a quick look at, here's kind of a visual representation of this, right? If we're going to take the set of natural numbers we'll define as a capital N, you might want to just, I mean, you could go ahead and include those on your little study guide. And this is, you're not going to turn this in. If it's got 3 holes on it, it's just for you to use as notes, right? So when we're writing the letters that represent the sets, the set of natural numbers is a capital N, the set of whole numbers is a W, the set of integers is not an I, usually we want to call it a capital Z, and the set of rational numbers we call capital Q. Now notice how they're related. Does this make sense? Right? The biggest set is the set of rational numbers, but contained inside the set of rational numbers is the set of integers, right? Because aren't the numbers like, for example, -3 and -2 and -1? Those are fractions. What's on the bottom of the fraction? 1. We don't really write it, but it's there, isn't it, right? We can write them as fractions. And contained inside the set of integers are some other numbers, the whole numbers, right? And the natural numbers. Does that make sense? So 3 is a natural number and a whole number and an integer and a rational number because it's contained in all those sets at the same time, right? We got these nested subsets, okay? Now what about all the numbers real numbers that can't be written as fractions? If all the real numbers that can be written as fractions we call rational numbers, what do you suppose we call all the real numbers that cannot be written as fractions? Irrational. There you go. And notice that the set of irrational numbers is outside of and separate from the set of rational numbers, right? Would you agree that rational numbers are not a subset of irrational numbers, right? An integer like -3, that's included in the set of rational numbers. It's a subset. So -3 is an integer and it's also a rational number. But something like 1/2, that's a rational number, that's not included in irrational numbers. Irrational numbers, remember, are those numbers that cannot be written as fractions. So they're mutually exclusive. They're totally separate. They do not overlap, right? Okay, so here's our definition. Irrational numbers, how do we read this? It's the set of H such that H is not a rational number. That's it, right? Okay, what happens if we write irrational numbers as decimals then, do you suppose? If rational numbers either have to repeat or terminate, and irrational numbers are all the numbers that are not rational, what must they do? They go on forever, so they never terminate. What else? Can they repeat? No, if they repeated, they'd be rational, right? So they can't repeat and they can't terminate. Okay, make sense? All right, so let's summarize all this stuff real quick. Would you agree that these are all rational numbers because they can be written as fractions? If I write them as decimals, I'll just leave this on the notes, but either they're going to repeat. Now, what does that mean when I have a bar over that whole group of numbers? Okay, that's the group under the bar that's going to repeat, right? Good. So either that's going to be a repeating group, or it's going to be, in this case, it just turns into an integer, right? Which is a really simple rational number, or it's going to terminate as a decimal, okay? What about these 5 examples? Tell me, are they rational or irrational? First one is what? It's rational, because what does the square root of 25 simplify to? 5, right? And 5 is rational, okay? What about the second one? I would say this falls into the category of duh. Well, hold on, look how it's written. Okay, who's that for? Oh, she's not here. How's that written? It's a fraction, isn't it? So is it rational? Yeah, it's written as a fraction, so that has to be rational, right? How about the square root of 11? Irrational. That's different than the square root of 25. Now, what's special about 25? It's a perfect square, isn't it? Right? The square root of a perfect square is always going to be a whole number, right? And so that works out to be rational. But 11 is not a perfect square. That's going to be irrational. Okay? And what about 17/24? So obviously that's a fraction, so that's rational. What about that bottom one? That's tricky. Rational or irrational? Because you see a pattern? Okay, but is the pattern repeating? So there is a pattern, but because it's not repeating, it's irrational. Okay? All right, so here's our summary. Now, one thing I can do to make this a little better, I think this helps, right? If we say that the set of all real numbers is included in this red box, then here's a good representation. We've got the set of rational numbers and all of its subsets separate from the set of irrational numbers. Okay, here's just another representation. It says essentially the same thing. It's colored, so it's kind of nice, right? You've got the set of real numbers is the whole, everything combined. You've got the green set of rational numbers and its subsets separate from the red set of irrational numbers. Okay? I'm going to skip that one. We'll come back to that one later in the year. So let's just summarize then. I didn't say this, but what do you think the letter is that we associate with real numbers to represent the set of real numbers? Capital R for real. Okay. And then we already said, I think I gave you all these. Irrationals, that's Q prime, right? Q is rational, integers are Z, whole numbers W, natural numbers N. Real quick, what are some examples of irrational numbers? Just throw some different types of, just pi would be a good one, right? If we take pi out as a decimal, it just goes forever, it never repeats, never terminates. What else? Square root of 11, or square root of 2, or something like that. Good. As a decimal, something like, there's no bar there. It goes on forever, but it never repeats, right? Rational numbers. Square root of 25. How about I'll even do one better than that? How about if we do something like the square root of 4/9? If I simplify that, what's it become? Square root of 4 is
2/3.
2/3, yeah. 2 on the top, 3 on the bottom, right? So that would be a fraction, so that is rational. We could do like 1/2. We could do something like as a decimal, 0.25, it terminates. We could do 0.3 repeating, it repeats, okay? Integers, I'll skip those, we already know what those are, right? All the hash marks on a number line, whole numbers 0 plus the natural numbers 1, 2, 3, 4, etc. We already defined all those. Okay, where do they go up here? If those are my symbols, where does the R go, capital R? Okay, I'm hearing it. Just in the box, represents everything in the box. Okay, what about Q prime? Ah, good, that's gotta be the left one, doesn't it? Because it's by itself. Where would the Q go? Good, there's Q, very good. Then the next smallest subset would be integers, right? And then whole numbers and the natural numbers are the smallest. Good, okay. Let's see, Sarah? Let's see, watch this over. Okay. All right, so real quick, I don't want to do too many of these because you'll get the hang of it. We want to name all the sets to which each value belongs, right? So what's a good strategy here? Let's take -10. What's the smallest subset that it's a part of? Integers, good, because it's not a whole number and it's not a natural number. So we know it's an integer, but if it's an integer, if we look back at our diagram here, if it's an integer, then it's also included in the set of rational numbers, and everything's included in the box of real numbers, right? So if it's Z, it's guaranteed to be Q and R. What about 7? Pi minus pi simplifies to what? 0. So what's the smallest subset it belongs to? Whole numbers. But if it's a whole number, then that's included in the set of integers, which is included in the set of rational numbers, which is included in the set of real numbers, right? Okay, how about the square root of 30? Is 30 a perfect square? No, it's not, is it? So what's that going to be? Q prime. It's irrational, but everything, rational and irrational, are both included in a set of real numbers. So Q prime and R, right? Okay? All right, last little issue. So properties of real numbers. Okay, so these are, pretty simple. You've seen these things before, but you may have forgotten them. And I wouldn't blame you if you did. I'm going to give you a little hint here about how to really hang on to the important things in classes as you go through school and through life. How do you internalize and keep stuff in your brain? Well, the way to do it is not to think of them as facts. Okay, contrary to popular belief, flashcards are terrible. I mean, they're good for memorizing facts, but I once knew all 50 state capitals at some point in my life. Now I know like 5, right? I mean, I don't know, how come? Who cares? Right? I Google it if I need to find a state capital. That's not a big deal. That's not important information. It's low-level information. But, I can math and calculus. I don't always remember all my trig identities, but I can quickly derive any one that I want to. And give me a piece of paper, and I can derive all the trig identities in 30 seconds, right? Any one I want. Because I know the concepts. There's some processes and concepts there that are much bigger that are in my brain for good. Even though I might forget over the course of the summer, I might forget the individual identities because I don't use them very much over the summer. I never use them over the summer, right? You get the idea. So the point is you want to try to connect things using concepts and not individual facts. Okay, what about the commutative property? Well, it says the commutative property, and think about this in terms of a flashcard. If on one side of the flashcard you have commutative property of addition, and on the other side you have A plus B equals B plus A, you're going to forget it, right? Think of it this way, though. What's it mean to commute? Your parents commute to work. Where do they start their day? At home. And then they go to work, and then they come back home in the evening, right? So what have they done? They've just exchanged their place, right? That's what commute means. You're just going to exchange your place, okay? So the commutative property of addition just says that if I'm adding up two things, it doesn't matter the order in which I add them. I can commute the positions of the things that I'm adding. So A plus B is the same as B plus A. 3 plus 4 equals 4 plus 3, right? Same for multiplication. If I'm multiplying two things, I can commute the order in which I'm multiplying those. A times B equals B times A, right? 3 times 4 equals 4 times 3. Does that work for subtraction? No, it does not. One wrong. There we go. For subtraction, 17 minus 5 is different than 5 minus 17. Does not apply. Doesn't apply to division. 20 divided by 5 is different than 5 divided by 20. So the commutative property only applies to addition and multiplication. Okay, the associative property. What's it mean to associate? What do you associate with? Probably. You're typically probably your friends, right? People, your teammates, if you're playing a sport. If people are in business together, you call them business associates. How come? Because they're business people that have grouped together, right? So to associate means to group together. So all this says is that when I'm multiplying or adding more than two things at the same time, it doesn't matter how I group those things. I always have to multiply or add in pairs, but the order in which I group those pairs is irrelevant. Real quick, what's the answer? 2 times 3 times 4. 24. How'd you do it? Okay, 2 times 3 is 6. So you group those together. You associate 2 times 3 first. 2 times 3 is 6. Times 4 is 24. Anybody do it differently? But can anybody do it differently? How else did you get 24? 3 times 4 is 12. Times 2 is 24. Right? It doesn't matter, does it? I can associate the pairs that I'm multiplying or adding in any order I want to if I've got more than two at a time. Agreed? So in other words, A times the quantity B plus C is exactly the same thing as the quantity A times B times C, right? A plus the quantity B plus C equals the quantity A plus B plus C. I can group those, I can pair up those three in any order I want to for addition and multiplication. Does it work for division and subtraction? No, it doesn't. For example, if I do 8 minus 3 minus 15, if I group them this way, 8 minus the quantity 3 minus 15 is going to end up giving me 20. If I group them this way, the quantity 8 minus 3 minus 15, I'm going to get negative 10. Different results. Doesn't apply. Same for division. 64 divided by the quantity 8 divided by 4 is different than the quantity 64 divided by 8, then divided by 4, right? So once again, doesn't apply. Okay? Distributive property, I'm just going to skip over. You guys know this. You've done this more than any of them. And the reason you remember this, even though arguably it's maybe the hardest of all these, is because you've used it in terms, you can connect it to an algebra concept, which is stuck in your brains. How many times have you seen teachers do that, right? You're just distributing, okay? Okay, how about these last two properties, the identity properties and the inverse properties? We can connect these two together also. Think about what identity means. Your identity as a person describes your complete value as a person, right? It's a big, complicated thing. Okay, for math, it's a little bit easier. For numbers, the value is what the number is, right? So let me ask you this. What's the number, the special number that I could add to anything and not change it? 0. So we'd say that 0 is the additive identity number, or the additive identity. That's what I add to something to preserve its identity. What's the number I could multiply by something and leave it unchanged? 1. So the multiplicative identity is 1. Easy, right? There's your properties. Additive identity property, A plus 0 is A. Multiplicative identity property, or the identity property for multiplication, A times 1 is A. Okay, the inverse property. The inverse property is linked to this. Now fill in the blank for me. Let's say I've got some number like 5, okay? The goal of the inverse property is I want to get for my answer the special identity, additive identity, 0. So 5 plus blank equals my special number 0. 5 plus blank equals 0. Negative 5. Answer this one. Negative 11 plus blank equals 0.
Plus negative one, plus one.
Positive 11. Okay, so what did you do? What's the relationship between 7 and negative 7? They're opposites. There you go. Okay, so one thing we know is that for the inverse properties, the additive inverse just means the opposite. The definition of an additive inverse is just an opposite. And the reason that we have that is because look what we're trying to get. We're trying to get 0 for our answer. What do I add to something to get 0? The opposite. The multiplicative identity, answer this one, fill in the blank. 2/3 times blank equals 1. That's my special identity number for multiplication. 2/3 times what equals 1? Think about that for a second. 2/3 times blank equals 1. But what do I have to do to cancel the 2 and the 3? Okay, I need a 3 on top to cancel the 3, right? 2 on the bottom. What do we call that? The flip of a fraction. What do we call that? Reciprocal. There you go. Okay? Right? So the multiplicative inverse is just the reciprocal of the number. And why do we multiply by the inverse? Because our goal the whole time was to get back 1, the special identity number for multiplication. Okay? All right. Last issue. Can you tell me real quick what, we're going to probably maybe not quite get through the last couple of minutes. That's all right. What property is illustrated here? Think about that for a second.
Muted.
Okay, okay, is it? Dissociative, right? How come? Because we're multiplying more than 2 things. We're multiplying 3 things, and we're just grouping them in different orders, aren't we? You see the difference? So this would be the dissociative property of multiplication. Okay? Compare that to number 16. What's that? That's commutative, isn't it? I'm adding up 2 things, and I'm just exchanging the order in which I'm adding them. Right? Just changing places. So that would be the commutative property of addition. Okay? How about 17? How many things am I adding total there? I'm adding 3, aren't I? What am I doing differently? Grouping them differently. I'm associating them differently. So that would be associative property of addition. Okay, how about 20? Okay, now this time I'm adding something to get the same identity I started with. There you go, good. So it's the identity property of addition. You get the idea? Okay? All right, so the very last thing then, or maybe just one other one real quick here. How about for 2/3? What's the additive inverse of 2/3? Additive inverse just means what? Reciprocal, or no, hang on, additive inverse. You did the harder one. You did the multiplicative inverse is the reciprocal. So multiplicative inverse would be 3/2. Negative 2/3, just the opposite, right? Okay. Last issue. This is kind of a cool one. We'll close on this. So the closure property. This is a little different. We say that a set is closed under an operation, meaning it's closed for an operation. If when you do that operation to elements of the set, the answer is still inside the set. So that's a lot of words. Think about it in terms of an example. We want to answer the question, is the set of integers closed under multiplication? In other words, if I take 2 integers and I multiply them, will I always get back an integer? It is. That's true, isn't it? You can find no counterexample. You can never find an example where that's not true. So, we would say, what times am I gonna do that? So we would say that the set of integers is true, that it is closed under multiplication. Okay? If I multiply integers, the answer is still inside that set. What about the next one? The set of irrational numbers is closed under subtraction. Can you find, I can find lots of examples where that's true. The square root of 3 minus the square root of 2 is still some crazy irrational number, right? Can you find, how many counterexamples do I have to find to disprove that? Just one. If I can find one example where it's not true, then it's false. Can you find a way to subtract two irrational numbers and get back a rational number? Give you a hint. The two numbers, the two irrational numbers, don't even have to be different. We would say number. So what if I did something like, say, pi, which is irrational, minus pi? What's that give me? 0. That's rational, isn't it? So it's false. Taking two irrational numbers and subtracting them does not guarantee I'm going to get back another irrational number. Whole numbers are closed under division. That's a pretty easy one to disprove. Think of two whole numbers I could divide and get back a non-whole number. About any of them, really. Almost any. 4 divided by 2 wouldn't work. 4 divided by 2 is 2, which is a whole number. That seems to prove it, but give me one example where I get a result that's not a whole number. What do you think? 73 divided by 26. Okay? Or even something simple like 2 divided by 3 is 2/3, right? That's not a whole number. So that's false. Odd numbers are closed under addition. 5 plus 7, what's that equal? 5 plus 7 is 12. Is 12 equals 12 odd? 12 is even though, isn't it? So if I take two odd numbers and add them, I don't necessarily get back an odd number.
Please excuse interruption.
So false.
Just a reminder, tomorrow is picture day. Your picture will be taken
Oh, picture
for
day.
your English period.
That's nice.
Even if you do not wish to purchase.
So I made a bunch of worksheets. I'm not going to give them to you. I'm just going to hold off. I got to build a couple more problems in Moodle, but I'll give you a Moodle assignment instead.
Again, tomorrow is
Way better for
picture day.
you, way quicker, easier to do. So it may not be ready tonight, but don't worry, it won't be due until, let's say, Monday or so. See you up on the time. Okay? All right. Have a good afternoon. Go enjoy the sunshine.